In the last few lessons, we've looked at finding polynomials for functions in some kind of random ways. For sine x, I just gave you the terms, and then in the last unit we were making them look like geometric series or using the fact that we knew what sine, the polynomial for sine x looked like. Well, in this video we're going to find a systematic way to find a Taylor polynomial that will match any function. So let's start here. We're just going to start generically first of all. Find a quadratic function f such that these things are true. So when we talk about a quadratic, we think about it this way. I'm going to use a brighter color so it looks very much different. So we think about it this way. F of x, ax squared plus bx plus c. That's a quadratic, of course, a generic. However, the way we've been looking at these polynomials, these Maclaurin polynomials, is that it starts with the least degree. So this quadratic is in descending order, the highest degree down, but polynomials that we've been writing for this unit have gone in ascending order. It's just easier to find. So when we're looking for then is this polynomial. All right, first thing they tell us is that f of 0 equals 3. Okay, that's good. F of 0 equals 3, so we know that 3 is equal to c plus b times 0 plus a times 0 squared. So now we found the c value. C is equal to 3. All right, we're going to be a little bit more methodical for the next one. F prime of 0 is negative 2 is the next condition. So we're going to try to be methodical. We're going to look at the pattern here because we're trying to get a systematic approach. So if we say, we know that f prime of x then will be b plus 2 times a times x. All right, so we know that negative 2 will equal b plus 2 times a times 0. So now we found that b in this quadratic is the first derivative. Okay, let's keep going. The second derivative at 0 equals 4. All right, if we look at the second derivative, now bear with me here, this is going to seem a little obvious to you, but the derivative of b is 0. For 2ax, I need to use the power rule. So I have 2 times 1, because that was the exponent of x, and there's a reason I'm doing this, times a. All right, the second derivative is equal to 4 when x is 0. 2 times 1 times a. So a is equal to the second derivative, which was 4, divided by 2 times 1. There's a reason for why I did that. I'll simplify it and I'll put it into the equation the right way, but now we found that a is equal to 2. All right, so I can write this function. I can write this quadratic. I know that c is 3, b was negative 2, and a was positive 2. It was the second derivative divided by 2 times 1. There is a quadratic that fits all of that criteria. I'm going to give you another one now. I'm going to ask you to find a cubic function, and I want you to think about the pattern again. I want you to do exactly what I did. Don't just go through the motions of the power rule, but actually write out the power rule, because I think you're going to start to see some patterns here. So here we go. Find a cubic function f such that all of these things are true. So I'll give you a minute to go give it a try. Okay, welcome back. We are looking at a cubic function this time. Cubic function is d plus cx plus bx squared plus ax cubed. All right, f of 0 equals negative 1. So we know that negative 1 equals d plus c times 0 plus b times 0 squared. I don't need to read everything I'm writing, sorry. So we know that d is equal to -1. I'm going to save some space because I'm going to need it. d is -1. All right, now let's look at the first derivative. I'm going to be methodical here and think about the coefficients. So the derivative of d is 0. C, it's really, I mean, if we're going to be methodical, this is 1 times c. And then for b, that's 2 times b times x plus 3 times a times x squared. And if we replace all of those x's with 0 and f prime with 5, we end up with c equaling 5. Or let's be more specific, 1 times c equals 5. So c equals 5 divided by 1. This was the first derivative divided by 1. Okay, let's go on to the next one. F double prime of 0 is 1/5. All right, the second derivative then, we're going to be methodical again. 1 times c, that's 0. Then we have 2 times 1 times b times, no x's anymore because that is 0, plus 3 times 2 times a times x. Now, if we replace all of the x's with 0, we end up with 2 times 1 times b. So b is equal to, and I'm going to write this in a really horrible way, 1/5 divided by 2 times 1, or the second derivative at 0 divided by 2 times 1. All right, third derivative then. I hope you're starting to see the pattern. The third derivative is -12. We'll simplify all of this later. I'm just trying to get you to see the pattern. So the third derivative then is 3 times 2 times 1 times a. And if this is -12 when x is 0, then we know that a is equal to -12 over 3 times 2 times 1. I hope you're starting to see this now. So this is the third derivative divided by 3 times 2 times 1. Okay, so we found d. d was just f of 0. We found c. c is f prime of 0 over 1. I'm going to write it out this way. f of x was d, which was we found to be f of 0. And then c was f prime of 0 over 1 times x. b we found to be f double prime of 0. Are you seeing the pattern yet? I hope you are. And then this is x squared. And then the third one is the third derivative divided by 3 times 2 times 1, x cubed. So now to actually put in the values that we need. If you're not seeing the pattern, I'll do it in the next one. F of 0, so now we've got -1 plus 5x, and then 1/5 over 2 becomes 1/10. -12 divided by 3 times 2 times 1, that's -2. All right, one more. A quartic, a fourth degree polynomial. I want to see if you can really find the pattern this time, and if you can, kind of like make this process a little bit shorter. So one more, find the quartic, and then we'll summarize this. Okay, welcome back. So the quartic, oops, still in highlighter mode. The quartic f of x is e plus dx plus cx squared plus bx cubed plus ax to the fourth. I'm going to go a lot faster this time, and we're just going to kind of cut to the chase. So we know that f of 0 is just going to be e. So in this case, oops, e is equal to 2. Then if we find the first derivative, we started noticing that pattern, that the d value is, I'm trying to go too fast, is d times 1, and then all of the rest of these terms become 0 because b is 0, but I'm still going to write them because we're going to need them later. All right, so now we know that f prime of 0 is d divided by 1, which is negative 3 divided by 1 in this case. I wrote that wrong. Let me try it again. D is f prime of 0. Wow, I'm trying to go too fast. D is f prime of 0 divided by 1. So we know that d is going to be negative 3 over 1. F double prime, if we find the second derivative, we know that this is 2 times 1 times c. So if you haven't noticed the pattern, I'll help you notice the pattern. We're talking about factorials here. I hope I didn't just totally blow your mind. I hope you were starting to see that pattern. So if I look at the second derivative equaling 0, I know that c then will be the second derivative at 0 divided by 2 times 1, or divided by 2 factorial. So c is equal to 5 over 2 factorial. And if I may now skip some steps here, b is going to have the similar pattern where b is going to be equal to the third derivative at 0 divided by 3 times 2 times 1, or 3 factorial. So we know that in this case, b is negative 10 over 3 factorial. And finally, a is the fourth derivative at 0 divided by 4 factorial. So we know in this case, a is 4 divided by 4 factorial. That's a much faster way, and that's the systematic way of writing a polynomial, a Maclaurin polynomial. So we can take all of this stuff now and put it together and write our function. F of x equals e, which was 2, plus negative 3 over 1 factorial times x, plus 5 over 2 factorial, x squared, of course, these can be, and in most cases, if it's a multiple choice, you should simplify those coefficients, but for the sake of the pattern, I'm going to leave it just like this. Okay, let's see if we can put this in some kind of formalized way. I hope you're starting to see some of the patterns here. But to write oh, my apologies. I'm going to do this. Before we go on to the next one, we're going to write the general form for any Maclaurin polynomial. So any Maclaurin polynomial following the pattern that we found. Sorry, I went a little too far ahead. Can be written like this. So for whatever your function is, we say that there is a polynomial that will match it, or that'll come close to it. And in order to write that polynomial, we know that the first term will always be the function with 0 plugged in. The next term will be the derivative of that function at 0 divided by 1 factorial. And so on. Now, if we write this in a generic way, so if we're talking about any polynomial, as long as we can, out to the nth term, we would say we would take the nth derivative at 0 is the numerator of the coefficient. And then whatever that derivative was, that's the factorial, n factorial, and x to the n. So this is just the generic way of writing any polynomial. We write the first few terms. There are a bunch of terms in the middle. This is the generic, the nth term, but it keeps on going. This is just saying that's how you would write any term. But the dot, dot, dot is saying this polynomial can go on to an infinite number of terms. And that would make this the good match for that polynomial we were trying to write, or for the function we were trying to write. I'm going to stop here before I go on to the next one. I'm going to let you soak that one in. And then the next video, we'll start writing polynomials for other functions.